dark energy stands as one of the most confounding and transformative discoveries in modern cosmology, fundamentally reshaping our picture of what the universe is and how it evolves. Instead of acting like the familiar forms of matter and energy that generate gravitational attraction, this enigmatic component produces a repulsive effect that pushes the cosmic fabric outward with increasing intensity. Scientists estimate that roughly 68% of the universe's total energy content consists of this invisible force, even though no one fully understands what it is, how it behaves, or why it exists in the first place. Its influence reveals itself not on small or local scales, but across the enormous distances separating galaxies, where gravity's pull grows too faint to counteract the cosmic acceleration dark energy drives. Observational evidence indicates that the further away a galaxy lies from us, the faster it appears to be receding, suggesting that space is stretching more rapidly as distances increase. This conclusion contradicts long-held expectations that the universe's expansion should slow down due to the gravitational attraction of all matter contained within it. Instead, dark energy ensures the universe expands not only without cease, but at an accelerating rate, meaning that distant galaxies drift farther and farther away at speeds that eventually exceed even the speed of light. Importantly, this does not violate Einstein's laws of relativity, because the galaxies themselves are not racing through space faster than light. It is the fabric of space between us and them that continually elongates. Einstein's speed limit applies only to objects moving through space, not to the expansion of space itself, which is a different physical phenomenon entirely. Despite the progress researchers have made in measuring the effects dark energy has on cosmic structures, its origin remains deeply mysterious, and competing theories strive to explain its true nature. One prominent idea suggests that even a perfect vacuum is not truly empty. Quantum mechanics predicts that space continuously seethes with tiny fluctuations that spontaneously appear and disappear on unimaginably small scales. This so-called vacuum energy might provide the repulsive force required to explain cosmic acceleration. However, calculations of the expected amount of vacuum energy overshoot observational values by a factor of 10 to the power of 120, the most catastrophic mismatch between theory and measurement in scientific history. Because of this massive discrepancy, many physicists suspect that dark energy cannot be explained simply as quantum vacuum energy, but rather requires an entirely new kind of physics. Some theories propose the existence of a dynamic scalar field that permeates all of space, similar in concept to the Higgs field, but possessing exotic properties that produce a negative pressure, thereby forcing expansion to speed up instead of slow down. These hypothetical fields, sometimes grouped under the name quintessence, could vary with time, leading to different expansion rates throughout cosmic history. Other researchers propose altering Einstein's equations of general relativity so that gravity behaves differently on the larger scales. In these modified gravity models, gravitational attraction gradually weakens over huge distances, making it seem as though an additional repulsive force is acting on the universe, even though the effect originates from gravity itself. Distinguishing between these competing explanations represents one of the greatest scientific challenges of the 21st century. Observations with powerful telescopes such as the James Webb Space Telescope are designed to look deep into cosmic time, observing the behavior of the universe when it was far younger and less dominated by dark energy. If measurements of ancient galaxies reveal that the expansion rate differed significantly from theoretical expectations, this could provide crucial clues about whether dark energy has remained constant or evolved over billions of years. By comparing present-day acceleration with the conditions that prevailed shortly after the Big Bang, astronomers hope to identify the physical mechanisms responsible for the universe's accelerated growth. The stakes are incredibly high, because solving the dark energy mystery means understanding not only how the cosmos has expanded, but also how it will ultimately end. A universe where dark energy remains constant will expand forever, gradually cooling and dimming until galaxies vanish beyond each other's horizons and stars eventually burn out, leaving behind a cold and desolate cosmic landscape. If the strength of dark energy continues increasing, however, it could eventually overpower all gravitational bonds, tearing galaxies, star systems, planets, and even atoms apart in a hypothetical apocalyptic future known as the Big Rip. Thus, dark energy is not merely a footnote in astrophysics. It is one of the most dominant and decisive forces shaping the destiny of everything that exists. Before the end of the 20th century, the prevailing belief among cosmologists was that the gravitational pull of all matter in the universe would gradually slow down the expansion that began with the Big Bang. Most scientists assumed that if the cosmos contained enough mass, gravity would eventually reverse the expansion entirely, causing the universe to collapse in a catastrophic finale commonly referred to as the Big Crunch. For decades, this conclusion seemed unavoidable, grounded in the conviction that gravity was the dominant force shaping the universe's long-term fate. Yet, a stunning discovery in 1998 overturned that confidence and forced humanity to rewrite its cosmic expectations from the ground up. A team of astronomers studying distant Type Ia supernova stellar explosions used as precise distance markers found that these supernovae were dimmer than predicted, meaning the galaxies hosting them were farther away than they should have been if expansion was slowing. The implication was both shocking and undeniable. The universe's expansion was accelerating instead of decelerating. This landmark revelation suggested that some unknown force was driving galaxies apart faster and faster, overpowering the attractive nature of gravity across vast intergalactic distances. The moment this discovery was validated, the cosmic storyline changed forever. Instead of a future defined by collapse, the universe's evolution now pointed toward eternal expansion, reshaping not only scientific equations, but also philosophical concepts about existence and destiny. Prior to this groundbreaking finding, astronomers debated whether the universe's total mass density was above or below a critical threshold. A universe above that threshold was destined for collapse. One below it would expand forever, though at an ever-decreasing rate. The 1998 results shattered that framework by revealing a third unexpected possibility: expansion that grows progressively faster with time. The discovery required scientists to introduce a previously unknown energy component into cosmological models, what we now call dark energy, that constitutes the majority of the universe's content and drives its accelerated growth. With this new understanding, earlier views of cosmic history had to be radically revised. Instead of a simple tug-of-war between expansion and gravity, the universe's progression now appears to be divided into distinct eras. During the first several billion years after the Big Bang, matter both ordinary and dark was dense enough for gravity to win the struggle, slowing the expansion to a more moderate pace. However, as the universe grew and matter spread out, gravity's influence weakened while the power of dark energy rose. At some point roughly 5 billion years ago, this mysterious force became dominant, pushing the universe into its current era of ever faster enlargement. With that shift, our cosmic fate diverged from the path once predicted. The future no longer holds a dramatic collapse, but instead a quiet severing of cosmic connections, as distant galaxies are carried away at accelerating speeds until their light can no longer reach us. Over incomprehensible stretches of time, the universe will become increasingly vast, increasingly empty, and increasingly isolated. The galaxies that remain gravitationally bound to one another, such as those in the local group, will stay together and merge, but everything beyond will vanish from sight as expansion outruns even the ability of light to bridge the growing distances. This revelation carries profound consequences not only for theoretical cosmology, but for everything we understand about the universe's lifespan and ultimate destiny. If dark energy remains constant in strength, it will ensure an eternal deep freeze known as heat death, where stars extinguish, black holes evaporate, and the cosmos becomes a silent void. Should dark energy intensify with time, however, the outcome could be far more violent, potentially leading to a future where atoms themselves are torn apart, a scenario labelled the Big Rip. Astrophysicists remain determined to pinpoint which of these futures awaits us, as the answer depends entirely on the precise nature of dark energy. The discovery that launched this great investigation earned the 2011 Nobel Prize in Physics, highlighting the monumental significance of overturning centuries of gravitational assumptions. It also underscored a humbling truth. Despite the progress of science, the vast majority of existence remains hidden and unexplained. What once seemed like a universe where matter and gravity reigned supreme has now been revealed as a cosmos steered by a mysterious influence we cannot yet detect directly. In a very real sense, the 1998 discovery marked humanity's awakening to a wider and stranger universe than anyone had imagined, a universe destined not for collapse, but for endless, accelerated expansion, driven by a force that remains one of the deepest cosmic puzzles ever encountered. One of the most bewildering yet essential ideas in modern cosmology is that the expansion of the universe can make galaxies appear to recede from us at speeds greater than that of light, even though the laws of physics insist that nothing can physically move faster than light through space. The key to resolving this apparent paradox lies in understanding that galaxies are not rocketing away like spacecraft accelerating through the cosmic void. Instead, the very fabric of space connecting all points in the universe is stretching, carrying galaxies along with it. Einstein's theory of relativity places a strict speed limit on objects travelling within space, but it does not apply that same limit to the expansion of space-time itself. When astronomers observe distant galaxies, especially those billions of light-years away, they find their light spectra shifted toward redder wavelengths, a signal known as redshift, indicating they are receding from us. Edwin Hubble discovered that this redshift grows proportionally with distance, an observation later formalized into what is now called Hubble's law. The farther a galaxy is, the faster it seems to move away. In practical terms, this means that for every additional megaparsec of distance, about 3.26 million light-years, the expansion of space adds roughly 70 kilometers per second of recession speed. Over small distances, this effect is barely noticeable, especially when compared to the internal motion of galaxies influenced by gravity. Yet, when distances reach into the realm of billions of light-years, the cumulative stretching of space becomes enormous. Thus, galaxies far enough away do not merely exceed the speed of light from our perspective, they may be receding at multiple times that speed. As bizarre as this sounds, it does not break relativity, because relativity governs the motion of objects within space, not the motion of space itself. The expansion is analogous to dots painted on an inflating balloon. The dots are not moving across the balloon's surface, but the surface between them grows, causing them to separate. The larger the balloon becomes, the faster the dots separate, especially those near the edges. This inflating balloon analogy helps illustrate how cosmic acceleration results in galaxies slipping away faster than light can chase them, meaning their light will never reach us, regardless of how long we wait or how advanced our instruments become. There exists a boundary called the cosmic event horizon. Any object receding faster than the light it emits can travel toward us will remain forever unobservable. Beyond this horizon, information is permanently cut off from us, creating a fundamental observational limit to our knowledge of the universe. Even galaxies currently visible may one day vanish from sight, not because they cease to exist, but because cosmic expansion will eventually carry them beyond this horizon. Over trillions of years, observers in the Milky Way or whatever our galaxy evolves into will see fewer and fewer galaxies in the sky as the expansion speed continually increases. In the unimaginably far future, only our local galactic neighborhood, which is gravitationally bound, will stay together. Everything else will have disappeared into the unreachable darkness beyond our view. This makes modern astronomy uniquely privileged in cosmic history. We exist at a time when much of the universe is still visible. Future observers may not be as fortunate. They could conclude wrongly that their island of galaxies constitutes the entire cosmos, just as astronomers believed a century ago. The expansion rate's behavior over cosmic time creates further complications for distance measurements. The universe is only 13.8 billion years old, so one might expect its radius to be 13.8 billion light-years. But because expansion has continued while light travels, objects whose light began its journey billions of years ago are now far beyond the distance that light alone would suggest. A photon emitted when a distant galaxy was 13 billion light-years away arrives today from a galaxy that has since been carried to nearly 46 billion light-years distant. This seemingly contradictory situation arises because the slowdown or acceleration of expansion has changed over the universe's lifetime, requiring astronomers to account for dynamic space-time growth when estimating distances. Measuring cosmic scales becomes a constant exercise in translating between what we see, light from the past, and where objects actually are now. Every telescope image of a galaxy is not a snapshot of its current location, but of where it was when its light first set out. Thus, The universe we observe is always the universe of yesterday, never the universe of today. Even the closest star system beyond the Sun, Proxima Centauri, appears to us as it was 4 years ago. When we look at Andromeda, the light hitting our eyes began travelling before modern humans existed. And when we detect the most distant galaxies ever found, we are witnessing cosmic structures as they appeared mere hundreds of millions of years after the Big Bang. To grasp the true scale of the universe is to accept this temporal displacement. Distance is time, and time is distance. The expansion of space ensures that the cosmos never stands still long enough to be measured simply, and every number cosmologists compute is bound up in both what was and what is yet to come. The paradox of faster-than-light recession is therefore not a violation of natural law, but a direct consequence of a universe that refuses to remain static, constantly stretching the limits of observation and reshaping our understanding of reality itself. In the earliest chapters of cosmic history, dark energy played virtually no role in shaping the universe's behavior, because matter, both visible and invisible, was packed together far more densely than it is today, creating a much stronger gravitational pull that slowed the initial expansion after the Big Bang. Gravity governed everything. It moulded primordial gas into stars, stars into galaxies, and galaxies into immense clusters bound together through mutual attraction. But as the universe expanded over billions of years, matter became increasingly diluted while dark energy remained pervasive and uniform everywhere in space. Eventually, a pivotal tipping point was reached, a moment when gravity's influence diminished enough that dark energy could take command of the cosmic expansion. This transition occurred relatively recently on the cosmic calendar, roughly 5 to 6 billion years ago, transforming the universe from a decelerating system into one accelerating outward at an ever-increasing pace. Since that epoch, dark energy has become the primary architect of cosmic structure on the larger scales, ensuring that the universe grows emptier and more stretched out as time progresses. Because dark energy's repulsive effect strengthens with the expansion of space, its influence continues to intensify, widening the vast distances between galaxies so quickly that many of them will eventually slip beyond any possible contact. Galaxies that are gravitationally bound into clusters will remain together, merging into massive conglomerates over trillions of years. However, galaxies not part of such systems are destined to drift into isolation, disappearing from view as their light becomes unable to outrun the accelerating expansion. This dynamic ensures that the universe's current richness and variety of visible structures is temporary. The cosmic web, with its filaments linking clusters across immense regions of space, will gradually dissolve as the threads stretch farther and farther until every major grouping becomes effectively alone in the night. Ideas that once dominated cosmological theory, such as the possible future collapse of the universe, now seem increasingly implausible, given the overwhelming persistence of dark energy's push. The notion that gravitational attraction might one day halt expansion has been replaced by models in which expansion never ends. Yet uncertainties remain, because the true nature of dark energy is still hidden from our understanding, and its long-term behavior remains one of the greatest unknowns in physics. If dark energy has a perfectly constant density in space and time, a property that resembles Einstein's original concept of a cosmological constant, then expansion will continue accelerating forever, creating a universe that slowly cools as stars exhaust their fuel and galaxies fade into darkness. In that scenario, time stretches on into a bleak era known as heat death, where every source of usable energy has been spent and the cosmos becomes a silent frozen abyss dotted only with remnants of astrophysical objects long past their prime. On the other hand, if dark energy gradually increases in strength, the universe may face an even more dramatic and catastrophic future known as the Big Rip. In this hypothetical ending, acceleration intensifies until it tears galaxies apart, then star systems, then planets, and eventually even the molecules and subatomic particles that make up matter itself. Everything from the largest galaxy superclusters to the smallest quarks would be forced apart in a final act of cosmological disintegration. There is also the slightest possibility that dark energy might weaken or even reverse in behavior, although this outcome currently lacks strong observational support. If such a reversal occurred early enough in the distant future, gravity could regain control and pull the universe back together toward a collapse. While intriguing, this idea now sits on the fringe of theoretical discussions due to the mountain of evidence showing acceleration is both real and dominant. Understanding which future truly awaits us requires not just studying the cosmos as it is today, but investigating its entire history to see how dark energy evolved as galaxies formed and expansion transformed. Modern telescopes, advanced particle physics experiments, and precise measurements of cosmic background radiation all work toward the same goal: discovering whether dark energy is a static property of space or a dynamic phenomenon with changing effects over time. This pursuit is not merely academic, it is a quest to uncover the ultimate storyline of existence. The universe we inhabit is shaped by forces we cannot touch, see, or generate in laboratories, yet those forces dictate the grandest scale of physical reality. The rise of dark energy, as the dominant influence in the cosmos, marks a profound era in universal evolution, one where gravity's reign fades and the acceleration of space becomes the chief sculptor of the future. It is a reminder that the universe is not a static backdrop but a living, changing entity, with a destiny still being written and an origin that continues to defy full comprehension. One of the most astonishing problems in theoretical physics emerges when scientists attempt to describe dark energy as vacuum energy, the quantum fluctuations believed to pervade empty space. According to quantum field theory, even a region stripped of all particles is not truly empty. Instead, it seethes with transient virtual particles constantly appearing and disappearing. Every point in space supposedly contains this restless foam of quantum energy, and if we sum up the contributions predicted by modern theory, the resulting vacuum energy should be immense, so immense that it would cause the universe to expand with overwhelming ferocity. Yet observations show something altogether different. Dark energy does exist, and does drive accelerated expansion, but its measured density is astonishingly small compared to theoretical predictions. The mismatch between the expected and observed values is not just a minor discrepancy, it exceeds calculations by a factor of 10^-120, a number so outrageously large it dwarfs every other numerical disagreement ever encountered in physics. This immense gap has been called the worst theoretical prediction in the history of science, a sign that something about our understanding of quantum vacuum or gravity is profoundly incomplete. It is as if the universe has delicately fine-tuned the vacuum energy to be almost zero, but not quite zero, allowing galaxies, stars, and planets to form without being torn apart by rampant acceleration. If the theoretical value had been even a tiny bit larger, the cosmos would have expanded so fast that matter could never have clumped together. Conversely, if vacuum energy were negative and too strong, rapid collapse might have occurred, preventing cosmic evolution from reaching any complexity. The fact that the real value sits within such a narrow life-permitting range raises profound questions about why the universe is as gentle as it is. This enigma sits at the intersection of cosmology, particle physics, and philosophy, and no single approach has yet provided a satisfying answer. Physicists have proposed that perhaps vacuum energy does exist in the enormous quantities predicted, but some unknown mechanism cancels almost all of it out, leaving only a faint residue that manifests as dark energy. Others speculate the value of vacuum energy might vary across different regions of a hypothetical multiverse, with our particular cosmic domain being one of the rare places where the value allows galaxies and observers to exist. Still others argue that the entire theoretical framework behind vacuum energy must be reformulated, because current calculations assume contributions from quantum fields that may not interact with spacetime the way we think. Another approach attempts to refine the geometry of spacetime itself. In general relativity, gravity arises from the curvature of spacetime caused by mass and energy. Dark energy's effect resembles a uniform negative pressure that pushes spacetime outward instead of inward. Some theorists suggest that the equations connecting vacuum energy and curvature are incomplete or incorrectly applied at cosmic scales. If the gravitational response to vacuum fluctuations behaves differently than predicted, the enormous quantum value might simply not participate in cosmic expansion the way our equations currently assume. The crisis exposes a deeper issue. The fundamental theories governing the very small and the very large quantum mechanics and general relativity remain stubbornly incompatible with one another. Where quantum mechanics describes particle behavior in probabilistic waves, relativity describes the smooth geometry of spacetime. Dark energy sits awkwardly between these two domains, pressing them into a confrontation they cannot yet resolve. Until a unified theory successfully merges quantum physics and gravity, vacuum energy will be a towering mystery at the heart of modern science. The problem also demonstrates how much of the universe's true nature lies beyond the reach of our most trusted models. The successes of physics over the past century, from explaining electromagnetism to predicting black holes, give the impression that the laws of nature are well understood. Yet the vacuum energy paradox reminds us that beneath these triumphs lies a deeper layer of reality still hidden from comprehension. Every calculation that multiplies quantum predictions by 10^120 feels like a flashing neon sign indicating that something pivotal is missing. Dark energy, with its incredibly subtle but cosmically dominant influence, forces humanity to confront that missing piece. The hope is that solving this problem will lead not only to a clearer picture of dark energy, but also to a more complete and elegant theory of everything, a framework that fully unites the building blocks of matter with the structure of space-time. If such a theory is ever achieved, the baffling mismatch between vacuum energy theory and dark energy observations may come to be seen as the clue that ultimately unlocked one of the greatest scientific revolutions in human history. For now, however, the vacuum remains the most perplexing substance imaginable. Everywhere, infinitely energetic according to mathematics, yet inexplicably whisper-soft according to nature itself. Since the vacuum energy explanation fails so dramatically to match observations, many physicists have turned to entirely new theoretical frameworks in an effort to uncover the true nature of dark energy, arguing that something beyond our current understanding of physics must be at work. One of the most popular alternatives proposes that dark energy arises not from the vacuum itself, but from a previously unknown field spreading through the universe, similar in concept to the Higgs field that permeates all of space-time. These hypothetical fields, often referred to collectively as quintessence, could possess exotic forms of energy and negative pressure that dynamically influence cosmic expansion. Unlike the cosmological constant, which would remain unchanging throughout the lifespan of the universe, quintessence might evolve with time, meaning the strength of cosmic acceleration could vary across different eras. Observations seeking signs of such evolution could reveal whether the force now dominating cosmic motion is truly constant or gradually shifting. A related concept explores whether dark energy might be a manifestation of a more complex system of fields interacting over cosmic distances, generating repulsive effects only when galaxies become widely separated. These ideas rely on the notion that the vacuum is not the only fabric filling space. Unseen energy structures could ripple and stretch in ways that escape direct detection. Meanwhile, other theorists have chosen a different approach entirely. Rather than adding a new ingredient to the universe, they propose modifying the governing law itself, Einstein's general theory of relativity. Although relativity has proven remarkably accurate for explaining the motion of planets, the behavior of light, and the operation of GPS satellites, it has only been rigorously tested within a limited range of gravitational environments. On the largest cosmic scales, spanning billions of light-years, gravity might behave differently than Einstein envisioned. Modified gravity theories suggest that the apparent acceleration of cosmic expansion might not require an external repulsive force, but instead reflects a weakening of gravity across vast distances. In such models, the force binding the cosmos together fades more quickly than general relativity predicts, leaving acceleration as a natural consequence, rather than an anomaly requiring dark energy. Some variations of modified gravity also attempt to incorporate quantum effects into space-time geometry, aiming for a unified description of both the cosmic and the microscopic realms. If dark energy ultimately turns out to be a symptom of gravity that changes with scale, the concept of a separate mysterious energy might disappear altogether. However, distinguishing between true dark energy and modified gravity remains extremely challenging, because both explanations can be made to fit existing data reasonably well. Scientists must therefore pursue increasingly precise observations of cosmic expansion history, often using standard candles like Type Ia supernovae or standard rulers like baryon acoustic oscillations to detect subtle differences predicted by the competing models. Instruments such as the James Webb Space Telescope, the Euclid spacecraft, and the Vera Rubin Observatory are being built or already deployed with these kinds of measurements in mind. Beyond those strategies, Yet another group of theorists wonders whether dark energy might be an emergent phenomenon, a large-scale effect produced by the collective behavior of matter and gravity, rather than a fundamental force. In this perspective, the universe could behave like a complex system where interactions across immense scales generate properties that do not exist in smaller regions. The geometry of space-time could reorganize itself in unexpected ways as the cosmos expands, producing acceleration even without introducing entirely new physics. Some propose that our observable universe might reside within a larger extra-dimensional structure, meaning what we interpret as dark energy is actually gravitational influence bleeding in from higher dimensions. Others speculate that the large-scale uniformity assumed in standard cosmology may be incomplete. If matter is distributed differently than expected on the bigger scales, the observed acceleration might emerge simply from interpreting data under flawed assumptions. Yet each alternative, compelling as it may sound, faces its own conceptual or mathematical hurdles. Theories invoking new fields must explain why their effects remain invisible, except at enormous distances. Modified gravity approaches must work seamlessly across every scale from black holes to galaxies to the entire universe, without contradicting observations. Higher dimensional models must reconcile themselves with particle physics experiments, which have not detected signs of extraspatial directions, and emergent theories must demonstrate testable predictions that differ uniquely from the standard cosmological model. What makes dark energy such a formidable puzzle is not merely that its origin is unknown, but that every plausible explanation pushes against the limits of what we currently understand about reality. Solving this mystery will likely require revolutionary advancements in both theoretical insight and observational technology. The eventual resolution might merge quantum mechanics and general relativity into a single elegant framework, transforming humanity's perception of the universe as profoundly as relativity itself once did. For now, the hunt continues across laboratories and observatories alike, with physicists chasing faint signals from the earliest moments of time to unravel the cryptic force reshaping the cosmos. Whether dark energy proves to be a wholly new substance, a modification of gravity, a higher dimensional echo, or something beyond imagination, it promises to redefine the foundations of physics and deepen the story of a universe that is far richer and stranger than our ancestors ever dreamed. As astronomers seek to uncover whether dark energy has remained constant throughout cosmic history or evolved over time, one of their most valuable tools is the ability to observe the distant universe, which acts as a kind of time machine. The deeper we peer into space, the further back in time we see, because light must travel across expanding cosmic distances to reach our telescopes. This principle allows scientists to examine how rapidly the universe was expanding billions of years ago and compare those measurements to present-day expansion rates. If dark energy has changed in intensity or behavior, differences should be detectable when studying distant galaxies whose light has journeyed toward us since the universe was still young. The James Webb Space Telescope, along with several next-generation observatories, plays a crucial role in this exploration, due to its unprecedented sensitivity to faint ancient signals originating from epochs when matter was far more dominant and dark energy had not yet gained control. By measuring redshift, luminosity, and the distribution of galaxies in the early cosmos, Webb provides detailed snapshots of expansion dynamics at multiple stages of cosmic evolution. Any subtle deviations from the expected pattern could reveal whether dark energy is a static cosmological constant, as Einstein originally suggested, or a dynamic entity whose influence strengthens, weakens, or fluctuates over time. Meanwhile, complementary ground-based projects such as the Vera Rubin Observatory and the Dark Energy Spectroscopic Instrument, DESI, work to chart the large-scale structure of the universe across billions of light-years, mapping the cosmic web to detect how dark energy has sculpted its arrangement. These instruments measure baryon acoustic oscillations, faint ripples in the distribution of galaxies that serve as a kind of standard ruler for cosmic distances. By tracking how the spacing of these structures has changed through time, researchers can infer the rate at which expansion has varied. If acceleration was slower in earlier eras, dark energy may not be constant, which would dramatically reshape theoretical models. Cosmologists also rely on another powerful method, observing gravitational lensing, where massive objects like galaxy clusters warp the light of more distant sources as it passes by. This distortion allows scientists to trace the distribution of matter, both visible and invisible, across vast cosmic expanses. Since dark energy influences how structures form and evolve, mapping lensing patterns offers clues about its physical properties. Combined, these observational strategies create a comprehensive record of the universe's expansion history. They chart how cosmic structures stretched from the dense early universe to the sprawling, accelerated era we inhabit now. If a deviation emerges, if ancient expansion rates do not align with what a constant dark energy model predicts, then physicists would have strong evidence that the force propelling the universe outward is not fixed, but dynamic. Such a discovery would be transformative, implying that dark energy could eventually fade away or intensify enough to trigger outcomes more extreme than currently anticipated. The stakes could not be higher. Understanding whether dark energy changes determines how the universe will end. On one hand, if acceleration remains steady, galaxies will drift away from each other forever, leading to a lonely and frozen cosmic future. On the other, if dark energy strengthens over time, the expansion could spiral out of control, ultimately ripping apart galaxies, stars, planets, and even atoms in a final catastrophic event. Alternatively, if dark energy weakens in the distant future, gravity might reclaim dominance, potentially slowing expansion once again, though no compelling evidence yet supports such a reversal. The goal of every new observation is to tighten the precision of measurements, reducing uncertainties that currently leave room for vastly different interpretations. Humans find themselves living at a remarkable moment in cosmic history, not only because galaxies remain visible to us, but because technology now allows us to test ideas that once seemed purely philosophical. Instruments like the James Webb Space Telescope are not merely collecting data, they're actively probing the deepest mysteries of existence, searching for the very nature of the force-shaping cosmic destiny. Though dark energy cannot be directly seen or detected with laboratory instruments, its fingerprints cover the universe in unmistakable ways. Each supernova measured, each galaxy mapped, each gravitational lens analyzed adds a new piece to the puzzle. Bit by bit, the picture grows sharper as we push deeper into the unknown. The answers may not only illuminate the future fate of the cosmos, but could redefine physics itself, revealing new laws governing space-time, energy, and the grand architecture of reality. As scientists work to decode the expansion history etched into ancient starlight, they stand on the edge of one of the most profound discoveries imaginable, understanding why the universe expands the way it does and what that expansion means for everything that will ever exist. The ultimate fate of the universe depends entirely on what dark energy is and how its influence evolves over time, making this mysterious force not only a key to understanding cosmic history, but also the central factor that will determine how everything ends. If dark energy behaves as a true cosmological constant remaining, unchanged in strength indefinitely, then the future of the cosmos will unfold as an endless expansion, gradually stretching all galaxies farther apart until they slip beyond each other's observable horizons. In such a scenario, the universe enters a long period of decline. Stars exhaust their fuel and fade one by one, galaxies grow dimmer and quieter, new stars cease to form as the raw material for star birth becomes depleted, and the cosmos drifts toward a cold, thin emptiness. Over unimaginably long timescales, the temperature of the universe would inch closer to absolute zero, a state of heat death, where usable energy is so evenly spread out that no structure, process, or life could continue. This bleak future, while dramatic in scale, is a quiet one, where everything simply grows farther apart, colder and darker. Yet the destiny of the universe could be far more violent if dark energy is not constant, but grows stronger with time. In this more extreme possibility, the accelerating expansion would continue escalating, eventually overpowering even the strongest forces known to physics. First, galaxy clusters would lose their gravitational bonds, drifting apart as expansion overwhelms their internal attraction. Next, individual galaxies would be torn from within, their stars flung away into isolation. Stellar systems would unravel as planets slipped beyond the reach of their suns. The destruction would escalate downward through the hierarchy of structure. Planets disintegrating, atoms pulled apart, molecules ripped into fragments, and finally the very building blocks of matter shredded into their most fundamental components. This hypothetical catastrophic ending is known as the Big Rip, an apocalypse driven not by fire or collapse, but by the relentless expansion of space. If dark energy continues strengthening, estimates suggest that the final moments of this cosmic disassembly could occur tens of billions of years in the future, although the exact timing depends entirely on how fast dark energy evolves. Other theorists have suggested intermediate outcomes that differ from both heat death and the Big Rip. In some scenarios, dark energy could remain constant for trillions of years, maintaining the universe in a state of eternal expansion without triggering disintegration at the smallest scales. The cosmos would become a landscape composed of isolated island universes, gravitationally bound clusters, or merged galaxies drifting alone in an ever-growing sea of emptiness. Light emitted from one cosmic island would never reach another, making communication and visibility across the universe impossible. Civilizations living within those islands would have no evidence that anything exists beyond the dim remnants of their own galaxy cluster, returning future cosmic knowledge to the limited perspective once held by ancient astronomers on Earth. This future highlights how uniquely privileged humanity is to exist in the current era, when cosmic structures are still visible and observable, and astrophysics can piece together a meaningful narrative of the universe. There are even more speculative possibilities suggesting that dark energy might not remain dominant forever. If the force were to slowly weaken with time or transition into a different form, gravity could once again begin to exert influence on the larger scales. In such a case, the outward expansion might eventually stall and reverse, leading to an inward collapse similar to the once theorized Big Crunch. However, current evidence overwhelmingly points away from this outcome, as observations consistently show acceleration continuing rather than slowing. Because the true nature of dark energy remains hidden, the future remains unwritten. It is possible that humanity currently stands near a tipping point in cosmic evolution without realizing it, just as astronomers before 1998 did not yet know the universe was accelerating. Theoretical physicists constantly probe whether dark energy interacts with matter or fields in unexpected ways, which could reveal hints of new fundamental physics and reshape predictions about the cosmic finale. The future of cosmology aims not only to chart how galaxies move today, but to decode the deeper truth of why they move at all. The fate of stars, planets, elemental structure, and perhaps even the notion of time itself is anchored to the answer. No matter which scenario ultimately proves correct, dark energy ensures that the universe will not remain in its current vibrant form forever. It stands as a silent architect shaping both the vastness of space and the destiny of every atom that exists within it. Humanity, living in a brief moment when galaxies remain visible and the cosmos still hums with energy, has only begun to grasp the power of the force directing the grandest story ever told, the lifelong evolution of the universe and its eventual end. When astronomers discuss the size of the universe, they must make a critical distinction between the portion we can see and the vastly larger realm that lies forever beyond our observational reach. The observable universe represents only the fraction of the cosmos whose light has had enough time to arrive at Earth since the Big Bang, which occurred roughly 13.8 billion years ago. Because cosmic expansion has stretched distances while that light was travelling, this visible bubble now has a radius of about 46 billion light-years, making the observable universe roughly 93 billion light-years across. Yet this immense sphere is not the full story. It is merely the tiny segment from which photons have successfully crossed the ever-expanding space separating those distant regions from us. The rest of the universe, potentially infinitely larger, remains hidden behind a horizon that even the most advanced telescopes will never penetrate. This limitation does not arise from technology or sensitivity, but from the fundamental physics of expansion. The speed at which space stretches increases with distance, meaning that beyond a certain point, galaxies recede faster than light can traverse the growing gap. As a result, their light will never reach us no matter how long we wait. It is as though the universe is divided into two kinds of places, those that can influence us through light or gravity, and those forever severed from our awareness by the accelerating expansion. Estimates suggest that the actual universe could be hundreds, thousands, or even infinitely times larger than the region visible to us. But those values depend heavily on the shape, geometry, and inflation history of space-time itself. Conditions scientists are still working to understand. This mismatch between what exists and what can be observed introduces a profound philosophical challenge. Everything humanity knows about the cosmos is derived from a limited sphere of visibility that shrinks each day in relative terms as expansion pushes more galaxies beyond the horizon. In the early 20th century, astronomers believed the Milky Way was the entire universe. Today we know our galaxy is only one of perhaps 2 trillion contained just within the observable region. That number might represent less than a tiny fraction of all galaxies that exist. In fact, the majority of reality may already lie beyond reach, slipping away faster than any future telescope or civilization could ever recover. Adding to this profound limitation is the fact that even within the observable universe, most matter and energy remain invisible. Dark energy constitutes about 68% of the cosmic inventory, while dark matter makes up another 27%. Ordinary matter, everything that forms planets, stars, living beings, and every object ever witnessed by science, comprises only about 5% of the total. Thus, what we can directly detect is not only spatially limited, but also represents a minuscule portion of what actually exists. This realization is akin to studying a vast ocean while confined to a small island, with most of its waters permanently obscured by fog. The enormity of the universe becomes even more staggering when considering the possibility of cosmic inflation, the brief but extraordinary burst of expansion believed to have occurred in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. During inflation, the universe expanded faster than any light signal could travel, ballooning from subatomic scales to astronomical proportions nearly instantaneously. This event may have stretched space so dramatically that what we observe today is just one minuscule patch of a much vaster entity that could extend far beyond the reach of any conceivable observation. Some inflationary models even propose that the cosmos might be infinite in size, or that multiple regions like our observable domain exist within a greater multiverse with differing physical properties. Though these ideas push against the limits of empirical evidence, they emerge naturally from the mathematics explaining the early universe's behavior. To understand cosmic size, scientists therefore rely not only on direct measurement, but also on theoretical insights that bridge the gap between what can be seen and what can be inferred. Every newly observed distant galaxy forces us to reckon with the reality that countless additional structures likely exist beyond them, unreachable due to the unbreakable constraints of space-time. The observable universe acts as a window, but the view is incomplete bounded by the finite age of the cosmos and the relentless expansion driven by dark energy. Consequently, when astronomers speak of the universe being 93 billion light-years across, they are referring only to the visible portion, not the true extent of existence. The full universe may be so large that the observable part is comparable to a single grain of sand on a beach, infinitely wide. Our cosmic horizon defines the limits of what we can know through observation, but not the limits of the universe itself. As expansion continues, the horizon tightens its grip on what remains visible, slowly erasing the grand structures we can currently study. We are living in a fleeting era when the universe's scale is still partially accessible to our eyes and instruments. In the far future, the cosmos will appear emptier and smaller, though in truth it will have only grown larger and more unreachable. The observable universe is therefore not the measure of everything that exists, it is simply the boundary of our current knowledge, while the true cosmos stretches far beyond, silent and unseen. Long before humanity recognized the staggering immensity of the cosmos, astronomers believed the Milky Way represented the entire universe, a lone island of stars surrounded by darkness without end. That assumption endured not because of a lack of curiosity, but because the instruments of earlier centuries simply could not resolve faint distant objects clearly enough to reveal their true nature. Many of the smudges scattered across the night sky, once catalogued as spiral nebulae, were widely thought to be small structures residing within our own galaxy. The revolution began in the early 20th century, but its seeds were planted even earlier through the meticulous work of a largely unrecognized pioneer, Henrietta Swan Leavitt. While studying variable stars known as Cephiids in the Magellanic Clouds, Leavitt made the groundbreaking discovery that the pulsation period of these stars is directly connected to their intrinsic brightness. The longer the period of variability, the brighter the star truly is. This insight created one of the most important tools in cosmic measurement, what astronomers call a standard candle, a class of objects with known luminosity that can be used to calculate distance. By comparing a Cepheid's observed brightness from Earth with its actual brightness inferred from its period, scientists could determine exactly how far away it must be. Leavitt's relationship, known today as the period luminosity law, opened an entirely new window into the universe by providing a dependable method for measuring astronomical distances far beyond the limits previously achievable. At the time, her discovery did not receive the recognition it deserved. She worked quietly at the Harvard College Observatory as one of the Harvard Computers, a group of women tasked with analyzing astronomical plates and data, while being excluded from much of the public scientific community. Yet her work would soon alter the very scale of the universe itself. A little over a decade later, Edwin Hubble applied Leavitt's method to determine the distance to the Andromeda Nebula, which many believe to be part of the Milky Way. With careful observations of Cepheids identified in Andromeda, Hubble demonstrated that this object was far too distant to reside within our galaxy. Instead, it was a separate island universe, what we now call a galaxy, containing billions of stars and existing millions of light-years away from the Milky Way. This discovery shattered the prevailing cosmic paradigm and confirmed that space was populated by an immense multitude of galaxies, each an independent collection of stars, gas, and dust. The universe, once thought to be modest in extent, suddenly expanded in human awareness to breathtaking proportions. Henrietta Leavitt's contribution provided the essential calibration that allowed astronomers to measure these vast distances, making her work foundational to every subsequent revelation about the large-scale structure of the cosmos. Hubble himself acknowledged that his discovery would not have been possible without her. Cepheids became the first rungs on the cosmic distance ladder, a hierarchy of measurement techniques built outward from our solar system into ever greater depths of space. As technology advanced, astronomers extended this ladder farther using additional standard candles and rulers, but the structure always relied on the precision first established by Leavitt's law. Her achievement continues to influence modern cosmology as researchers refine the Hubble constant, the rate of cosmic expansion, by tracking Cepheid variability with increasingly powerful telescopes, including the Hubble Space Telescope and now the James Webb Space Telescope, which can detect these stars at even greater distances. The role of Leavitt's insight in reshaping humanity's cosmic perspective cannot be overstated. It provided the key to realizing that our galaxy is just one among potentially trillions. It laid the foundation for Hubble's later conclusion that the universe is expanding. It helped transform astronomy into a science capable not only of cataloguing the heavens, but of measuring the geometry and evolution of space itself. Beyond its scientific implications, the story stands as a reminder of how profound breakthroughs sometimes emerge from places ignored or undervalued by the established scientific world. Leavitt worked without acclaim during her lifetime, yet her discovery enabled one of the most dramatic intellectual revolutions in history: the transition from a universe limited to the Milky Way to one filled with countless galaxies stretching across unimaginable distances. Today, every cosmic map, every discussion of dark energy, every inquiry into the structure and fate of the universe rests upon the ability to measure distance accurately on a grand scale, and that capability traces directly back to Henrietta Leavitt's careful study of flickering stars. Her legacy endures every time astronomers peer deeper into the cosmos and refine our understanding of just how vast reality truly is. Edwin Hubble's contributions did not end with proving that the Milky Way is only one galaxy among many. He went on to uncover a discovery so profound that it reshaped the entire foundation of cosmology. By examining the light from distant galaxies, Hubble noticed that their electromagnetic spectra were systematically shifted toward the red end of the spectrum, a phenomenon known as redshift. This shift occurs because wavelengths stretch as objects move away from the observer, similar to the way the pitch of a siren drops as an ambulance drives past. When Hubble compared the degree of redshift with the measured distance to each galaxy, he found a consistent relationship. The farther a galaxy was from the Milky Way, the faster it was receding. This observation led him to formulate what is now called Hubble's law, which states that the velocity of a galaxy's recession is directly proportional to its distance from us. In other words, space itself is expanding, carrying galaxies away from one another like raisins embedded in rising dough. Although individual galaxies are not travelling through space at high speeds on their own, The fabric of space-time is stretching, causing the distances between galaxies to grow over time. At the moment Hubble recognized this cosmic expansion, the scientific worldview experienced a dramatic shift from a universe that was long assumed to be static and eternal to one that is dynamic, evolving, and moving outward into ever greater size. This revelation also provided strong supporting evidence for the Big Bang theory, which proposes that the universe began from a state of extremely high density and temperature before expanding rapidly. If space is expanding today, then rewinding time must lead to a moment when everything was packed together in a single primordial state. As telescopes improved and astronomers measured more galaxies, the linear correlation Hubble discovered held with exceptional precision. What had begun as careful observations of spectral lines ultimately unveiled a fundamental property of the cosmos. Hubble's findings were further refined by subsequent scientists, including Georges Lemaitre, who had earlier proposed the theoretical foundation for an expanding universe, although his role was underappreciated at the time. Together, their combined ideas lay the cornerstone of modern cosmology. The measurement central to Hubble's discovery is the Hubble constant, which quantifies the rate at which the universe expands. Determining this number accurately remains one of the greatest challenges in astronomy, because different measurement techniques yield slightly different results, an ongoing tension now known as the Hubble tension. One method uses Cepheid variables, continuing the legacy of Henrietta Leavitt, while another relies on the cosmic microwave background radiation, the afterglow of the Big Bang. These two approaches provide expansion rates that disagree by a small but persistent amount. This discrepancy may not simply be due to errors. Instead, it might hint that our current cosmological model is incomplete or missing new physics. Regardless of the unresolved tension, Hubble's work definitively confirmed that the universe is not static. Instead of slowly winding down or remaining frozen in a steady-state configuration, the cosmos continues to stretch in all directions, changing with each passing moment. The most distant galaxies we observe today are also the oldest objects we can see, because their light has travelled for billions of years to reach us. Every time astronomers detect a galaxy farther away than previously known, they peek deeper into the universe's timeline, approaching closer to the era when galaxies first began to form. The expansion of the universe is not uniform in all environments. Within local galaxy clusters, gravity still dominates and holds systems together. That is why the Milky Way is not drifting apart from the Andromeda galaxy. Instead, the two are actually moving toward each other and will eventually collide. Expansion reveals itself only at large intergalactic distances, where gravitational bonds weaken. Hubble's insight therefore offered more than a measurement. It unlocked a new understanding of space itself. The universe is not an inert backdrop, but a flexible medium capable of stretching, evolving, and responding to the forces shaping it. This perspective radically altered scientific thought, requiring new equations, new models, and new interpretations of every cosmic observation. Hubble's discoveries also inspired generations of telescopic missions bearing his name, most notably the Hubble Space Telescope, which extended humanity's view deeper into the cosmos than was once imaginable. Through precise distance measurements and improved redshift surveys, astronomers have built an increasingly detailed map of the expanding universe, confirming that the cosmic fabric continues to accelerate under the influence of dark energy. Without Hubble's observations, the existence of dark energy might never have been recognized, and the accelerating universe could have remained an undiscovered secret. His work continues to shape how we study everything from supermassive black holes to the formation of large-scale structures stretching across billions of light-years. Ultimately, Hubble revealed the astonishing truth that the universe we inhabit is not a stable, permanent structure, but a growing, dynamic entity with a past, present, and future written into the movement of galaxies. His discovery marked the moment humanity understood that we are living inside a cosmic story filled with motion and change, a story still unfolding with every new observation and every new question asked about the nature of existence. As astronomy advanced throughout the 20th and 21st centuries, humanity's perception of the scale of the universe expanded in ways that earlier generations could never have imagined, repeatedly forcing us to revise our understanding of size and distance on a cosmic level. There was a time when astronomers proudly believed they knew the boundaries of existence, first the solar system, then the Milky Way, but each leap in observational capability shattered the limits placed on the universe by human assumption. What once seemed enormous soon appeared tiny within a newly discovered greater structure. When telescopes grew powerful enough to reveal galaxies beyond our own, the number of known stars multiplied by billions overnight. Later discoveries showed that these galaxies themselves were scattered unimaginably far apart across expanses of dark space, each containing not only stars but planets, nebulae, supermassive black holes and swirling arms of interstellar matter stretching for tens of thousands of light years. The sheer distances between galaxy systems dwarfed even the size of galaxies, introducing humans to an entirely new scale of magnitude. As astrophysical surveys scanned deeper into the sky, scientists recognized that galaxies do not float randomly, but instead form clusters and superclusters, connected by enormous filaments of gas and dark matter that weave the cosmos together like a vast three-dimensional web. Measurements of these structures revealed sizes stretching hundreds of millions of light-years across distances that made previous astronomical units feel absurdly small. Every time our tools improved, we saw farther, and every time we saw farther, the universe grew in our minds. Yet no matter how far astronomers looked, they found no physical edge or boundary. Space continued outward in every direction, filled with light from even more distant objects whose photons had spent billions of years travelling toward us. Observations from modern surveys suggest that the part of the universe we can detect, what we call the observable universe, contains roughly 2 trillion galaxies, each galaxy holding hundreds of billions of stars. If one were to count every star within that sphere, the total would surpass the number of grains of sand on all the beaches on Earth combined, and that enormous number still accounts for only the fraction we are able to observe. What lies beyond remains hidden from view, because light from those farther regions has not yet had time to reach us. This realization forces the conclusion that the true universe must be larger than anything science has yet documented. Even calling the observable universe enormous feels like an understatement when we acknowledge it is simply the portion accessible to our instruments during the universe's 13.8 billion year lifetime. Meanwhile, cosmic inflation theory proposes that the universe expanded exponentially during its earliest instant, suggesting that regions we will never see may outnumber the visible realm to a nearly infinite degree. Thus, the observable universe should be understood not as the universe itself, but merely as the limited window offered by physics and time. The human mind, designed for navigating everyday scales, a few meters, a few kilometers, struggles to grasp the absurd magnitude of cosmic distances. Light, the fastest entity in existence travelling at 300,000 kilometers per second, requires more than 8 minutes just to reach Earth from the Sun. Yet that same sunlight pales in comparison to the light that must cross the span of the Milky Way, taking about 100,000 years to do so. And that incredible journey becomes trivial when compared to light coming from galaxies billions of light-years away. When we observe objects from the distant past, we are seeing them as they existed when the universe was extremely young, because their light has been stretched and delayed by the expanding fabric of space. Thus, distance and time become inseparable concepts in cosmology. To look outward is to look backward, to witness the history of cosmic evolution imprinted on ancient photons. With each improvement in instrumentation from Earth-based observatories to space telescopes, the edge of visibility has been pushed farther, but never reached a true limit. Instead, we discover older and more distant galaxies, pushing the frontier of cosmic understanding ever outward. And yet, even as the known universe grows in our perception, humanity becomes increasingly aware that our knowledge remains tiny compared to the true extent of existence. The scale of the cosmos humbles every assumption that came before and erases any comfort in believing we occupy a central or special place. The universe challenges us with its immensity, inviting us to accept a reality far larger and more intricate than the human mind is naturally prepared to imagine. What began as a single galaxy became a universe filled with trillions. What once looked static and simple became dynamic, expanding, structured, and incomprehensibly vast. Each discovery widened our cosmic horizon, reminding us that wonder increases with knowledge, and that the true size of the universe remains one of the greatest questions still unfolding before us. As our understanding of the universe deepened, one of the most startling discoveries in modern cosmology emerged. Almost everything that exists is invisible and fundamentally different from the familiar matter that forms stars, planets, and living beings. When astronomers mapped galaxies and measured how fast they rotate, they realized that visible matter alone could not account for the gravitational forces holding these systems together. Without additional unseen mass, galaxies spinning as rapidly as observed should fly apart, flinging their stars into the void. This discrepancy gave birth to the concept of dark matter, an invisible substance that does not emit, absorb or reflect light, yet exerts gravitational influence on a colossal scale. Dark matter is thought to form vast halos surrounding galaxies, anchoring them gravitationally and allowing structures to grow over billions of years. It also forms the framework of the cosmic web, shaping the universe's architecture by pulling ordinary matter into dense clusters and filaments. Estimates reveal that dark matter constitutes around 27% of the universe's total mass-energy content, vastly outweighing the roughly 5% represented by atoms and molecules that make up every tangible object known to science. But even this astonishing fact pales in comparison to the discovery of dark energy, a mysterious force driving the accelerating expansion of the cosmos, accounting for about 68% of the universe. These two invisible components dominate reality, leaving ordinary matter to play only a minor role in the grand cosmic narrative. The implications are profound. Everything humans have ever observed, from ancient starlight to complex organisms, is just a tiny sliver of what exists. The visible universe is like a thin layer of frost on the surface of a deep and unseen ocean. Dark matter, although crucial to cosmic formation, remains undetectable by traditional means because it does not interact with electromagnetic radiation. Scientists infer its presence entirely through its gravitational effects. The motions of stars within galaxies, distortions of light due to gravitational lensing, and the growth of large-scale structures all reveal the pull of massive invisible quantities. Various hypothetical particles such as WIMPs, weakly interacting massive particles, or axions have been proposed to explain dark matter's properties, but none have yet been detected in laboratory experiments, leaving its true nature elusive. Meanwhile, dark energy appears even more mysterious. While dark matter pulls things together, dark energy pushes space itself apart, expanding the void between galaxies faster with time. It does not clump or cluster like matter. Instead, it permeates every corner of space-time uniformly, acting as a constant pressure that resists gravitational collapse. No experiment on Earth has directly measured dark energy, nor is there a consensus theory explaining its origin. It might be a property of the vacuum, a new field that fills the universe, or a sign that gravity behaves differently across cosmic distances. Whatever it is, dark energy controls the universe's fate, ensuring that galaxies continue drifting apart into isolation. That ordinary matter is such a small component of the cosmic inventory, challenges deeply rooted assumptions about significance and structure. Humans evolved in a universe where the visible elements seemed dominant, where stars illuminated the night sky and planets hosted life. Yet in the deeper cosmic truth, the familiar is not fundamental. The atoms that construct our bodies, the sun, the earth, every planet and nebula, all are merely residues left behind by more dominant and enigmatic counterparts. This realization reshapes humanity's understanding of its place in the universe. We are creatures of a minority substance, living on a rare kind of world, within a temporary window when galaxies are still visible to us. As time advances, dark energy will accelerate expansion so dramatically that many galaxies will slip beyond our sight, leaving future observers stranded in isolated regions, with no evidence that the universe once contained countless other islands of stars. If intelligent beings evolve billions of years from now, they may never discover dark energy or dark matter because the observable universe will appear empty and static. Cosmology itself could become impossible in the far future, its greatest truths lost not to ignorance, but to the relentless evolution of the universe. Today's scientists therefore stand in a unique era of cosmic discovery. They have just enough visibility to observe the structure of the universe and infer its dominant unseen components. By detecting the subtle gravitational signatures of dark matter and measuring the accelerating expansion attributed to dark energy, humanity has begun unraveling the true makeup of reality. Yet the more we learn, the more the cosmos appears dominated by forces that defy comprehension. The universe is not what it seems. The stars and glowing structures that decorate the night sky are only decorations on a stage built almost entirely from invisible actors. The quest to understand dark matter and dark energy represents one of the greatest scientific challenges of the modern age, promising answers that could revolutionize physics, redefine matter and space, and reveal the hidden nature of existence that has shaped the cosmos from the very beginning. As cosmologists mapped larger regions of the universe, they began to notice patterns that hinted at an astonishing truth. Galaxies are not scattered randomly through space, but arranged within colossal structures far beyond anything previously imagined. What appeared at first to be clusters of galaxies eventually revealed themselves to be parts of even larger formations, superclusters, walls, and filaments stretching across billions of light-years, creating a vast cosmic web that resembles networks of interconnected threads. The voids between these filaments are immense expanses containing almost no galaxies at all, making the universe look eerily like a sponge or neural network when viewed from afar. Some of the most remarkable of these formations include the Sloan Great Wall, discovered in the early 2000s and extending roughly 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, an even more massive structure whose estimated length reaches around 10 billion light-years. These discoveries challenge not only our intuition, but also our best theoretical models of how the universe formed after the Big Bang. According to standard cosmological theory, the universe began in a nearly uniform state with tiny quantum fluctuations providing the seeds for cosmic structure. Gravity then amplified those seeds over billions of years, pulling matter together while dark energy fought to push everything apart. However, there are limits to how large structures should be able to grow within the age of the universe. Given the finite speed at which matter can clump together, and the accelerating expansion stretching everything apart, it should be impossible for gravitational attraction alone to assemble structures larger than roughly 1.2 billion light-years. Yet observations repeatedly reveal formations that break this limit, forcing cosmologists to question whether our understanding of structure formation is complete. These superstructures are not merely large, they are so vast that light itself requires billions of years to traverse them. When astronomers study them, they're effectively looking at events that occurred in different epochs of cosmic evolution, stitched together into a single massive framework. The existence of such enormous patterns raises questions about the distribution of dark matter, which forms the scaffolding upon which visible structures are built. If dark matter is more smoothly or differently distributed than standard models assume, large-scale clustering could emerge earlier or grow larger than predicted. The survey of these immense cosmic features relies heavily on technologies capable of mapping the sky in 3 dimensions, measuring not only where galaxies appear, but also how far away they are. Redshift information allows astronomers to reconstruct their positions in space-time, revealing the grand tapestry hidden behind what otherwise looks like a 2-dimensional night sky. The more we map, the clearer the universe's intricate architecture becomes. And yet, with every discovery of a new enormous structure, the tension grows between observational reality and theoretical expectation. Some researchers suggest that these giant formations might not be single coherent structures, but rather alignments of smaller ones that only appear connected due to observational perspective. Others argue that their existence might hint at new physics, such as early cosmic inflation producing greater irregularities than previously assumed. In particular, the largest known structures strain the assumption that the universe is homogeneous and isotropic at the largest scales, an assumption that is one of the foundational principles of modern cosmology. The cosmological principle posits that while galaxies clump into clusters and voids exist, when one looks at a sufficiently grand scale, matter should be evenly spread throughout the universe. Giant formations billions of light-years long challenge the idea that such a smoothing scale exists within the observable realm. These discoveries force a deeper look into how dark matter guided the formation of the cosmic web, and whether new gravitational models or early universe phenomena need to be invoked. Regardless of theoretical tensions, these immense superstructures have transformed humanity's perception of the cosmos. They show that our galaxy is just a point within a cluster, which lies in a supercluster, which itself is part of a filament stretching across vast cosmic territory. The Earth, the Sun, and the Milky Way are unimaginably small pieces of an environment whose architecture defies comprehension. Even so, the cosmic web is not static. Dark energy continues stretching the universe, weakening gravitational bonds on the very largest scales. Over time, these grand patterns may disperse as galaxies fall out of contact and clusters drift apart. Future observers could be left unable to detect the true structure that once existed. Thus, humanity is living during a fortunate moment when the universe is both old enough to reveal its intricate patterns and young enough that those patterns have not yet disappeared into isolation. The discovery of gigantic cosmic structures underscores a profound lesson. The universe is far more complex, organized, and astonishing than anyone once believed, and it may contain architectural wonders even larger and stranger than those already detected awaiting discovery in regions near the edge of the observable frontier. To understand how the universe's grandest structures formed and to map them across cosmic time, astronomers have turned to some of the most powerful natural beacons in existence. Gamma-ray bursts, or GRBs, cataclysmic explosions marking the violent deaths of massive stars or the merger of compact objects like neutron stars. These bursts release more energy in a matter of seconds than the Sun will emit over its entire 10 billion year lifetime, making them visible across nearly the entire observable universe. Because they're so incredibly luminous, GRBs allow astronomers to detect galaxies so distant that their light has been travelling toward us for more than 12 or even 13 billion years. In this way, they act like cosmic lighthouses, revealing remote regions of space that would otherwise remain invisible. Observing their distribution provides clues about how matter was arranged in the early universe, when the first stars were forming and galaxies were beginning to take shape. Surprisingly, when researchers mapped the spatial placement of GRBs, they found that these explosions were not evenly distributed, but instead aligned themselves into vast patterns similar to those traced by galaxies and galaxy clusters. One particularly striking discovery involved a colossal arrangement known as the Hercules Corona Borealis Great Wall, a structure inferred through the clustering of GRBs on a scale stretching around 10 billion light-years, making it one of the largest known features in the cosmos. The existence of such enormous formations suggests that, very early in cosmic history, matter had already begun to organize into structures larger than current theories predict could form in such a short time. GRBs thus not only serve as probes of remote galaxies, but also challenge the assumptions behind standard models of structure formation, expansion, and the behavior of dark matter. Because GRBs originate from the deaths of some of the earliest massive stars, they carry within their afterglow chemical fingerprints of the primordial universe, allowing scientists to track how elements like carbon, oxygen, and iron spread through space as galaxies grew. Each gamma-ray burst becomes a momentary spotlight, illuminating a faraway region, briefly turning invisible galaxies into objects that can be studied before the afterglow fades away. In addition to mapping large-scale cosmic structures, astronomers use the time-delayed arrival of light from different wavelengths gamma rays first, followed by X-rays, then optical and radio signals to investigate how the expanding universe stretches those wavelengths as they travel. This provides direct insight into the metric of spacetime itself, and the way dark energy influences photon motion over billions of years. GRBs therefore perform a dual scientific role. They allow a window into the past while also enabling precise tests of cosmological models that describe the universe's growth. As technology improves, telescopes like NASA's Swift and Fermi missions, as well as ground-based observatories equipped with fast response systems, have dramatically increased the number of detected bursts each year. With more data, patterns become clearer, and cosmologists can refine maps showing how the larger structures evolved. Yet with these insights come deeper puzzles. The gargantuan scales indicated by GRB clustering appear to contradict the cosmological principle, which states that the universe should appear roughly the same in all directions when viewed at sufficient distance. If structures many billions of light-years across truly exist, parts of the cosmos may be more organized than predicted, implying that the initial conditions of the Big Bang contained larger fluctuations than assumed, or that gravitational interactions and inflationary dynamics behave differently from current expectations. Some scientists suggest that GRBs might be revealing not a single continuous entity, but multiple distinct structures coincidentally aligned, their connection only apparent from our observational perspective. However, others argue that the statistical significance of their clustering cannot easily be dismissed and may force a reconsideration of standard cosmological assumptions. Regardless of the debate, gamma-ray bursts provide one of the clearest means to probe the distant universe at extreme scales. They bridge astrophysics and cosmology, linking the deaths of individual stars to the shaping of the universe's colossal architecture. With future observatories such as the Cherenkov Telescope Array and next-generation space-based gamma detectors, scientists expect to discover even more bursts at earlier epochs, pushing our view closer to the cosmic dawn and refining our map of the cosmic web as it formed. Each GRB detected is a reminder that the largest structures in existence are built upon the explosive legacies of stars, and that the evolution of the universe, from small-scale events to grand formations, is deeply interconnected. In the flicker of a dying star's final moment, astronomers find not an ending, but a clue to the universe's greatest secrets, written across billions of light years. As astronomers confronted evidence of cosmic structures stretching billions of light years across space, they realized that what they were observing should not be possible within the standard model of cosmology. According to the current understanding of the universe's evolution, there are limits on how quickly gravitational attraction can assemble matter into large-scale formations. In the early universe, everything was packed tightly together, but the expansion driven first by inflation and later by dark energy rapidly increased distances, reducing the ability of gravity to connect distant regions. Matter could only collapse into large structures as fast as information limited by the speed of light could travel from one region to another. This constraint imposes a theoretical maximum size on cosmic structures, often described as the homogeneity scale, beyond which the universe should appear smooth and uniform rather than clumpy or patterned. However, enormous formations like the Hercules Corona Borealis Great Wall appear to exceed this limit by an astonishing margin. If its measured extent of roughly 10 billion light-years is accurate, then gravitational clustering must have progressed far faster than current models allow. These discoveries have triggered intense debate in cosmology because they challenge fundamental assumptions about the physics of the early universe. Some scientists propose that the giant structures we see today might be illusions created by projection effects, where multiple smaller structures aligned along our line of sight appear as one continuous entity. Yet repeated statistical analysis suggests that the probability of such a perfect alignment happening by chance is incredibly small. Others argue that the structures could be ancient formed so early that inflation imprinted extremely large-scale density variations that gravity later amplified. But this contradicts the idea that inflation smoothed the universe to near uniformity. If such immense structures existed shortly after the Big Bang, then the initial density fluctuations must have been more dramatic than currently assumed. Another possibility is that dark matter behaved differently in the universe's infancy than our models describe, enabling rapid clustering on colossal scales. Dark matter forms the invisible skeleton underlying galaxy formation, so if its properties vary over time, if it interacted differently with itself or with normal matter, then structure growth might accelerate. Some theories even propose that dark matter may consist of multiple components, some colder and more prone to clumping, helping form massive structures earlier than expected. A more radical interpretation suggests that the presence of such huge formations calls into question the cosmological principle, the foundational assumption that the universe is homogeneous and isotropic on the larger scales. Standard cosmology requires this principle to hold true because the equations describing cosmic evolution rely on it. But if the universe instead contains preferred directions or large-scale asymmetries, then our models might need dramatic revision. This could influence everything from the interpretation of cosmic microwave background patterns to the inferred behavior of dark energy. There is also the idea that gravity itself might behave differently across inflationary epochs or across extreme distances. Modified gravity theories suggest that the force could be stronger or more efficient at binding matter together at early times, allowing structures far larger than those permitted under general relativity. While such ideas remain speculative, they demonstrate how seriously the scientific community takes the challenge posed by these giant structures. Beyond theoretical implications, these discoveries have philosophical consequences as well. They remind us how small the portion of reality that we comprehend truly is, and how every scientific model, no matter how successful, remains provisional, subject to revision when confronted with new evidence. The more humanity learns about the universe, the more we encounter surprises that defy expectation. The largest cosmic structures ever found force us to confront the possibility that some aspects of cosmic evolution remain hidden behind a veil of assumptions not yet recognized as incomplete. Technology continues to refine our view of the cosmos, and upcoming surveys will expand the catalogue of mapped galaxies and gamma-ray bursts with greater precision than ever. If even larger structures are identified, or if existing ones are confirmed with higher accuracy, cosmologists may need to rewrite major components of the standard model. Perhaps the early universe was not as smooth as originally thought, or perhaps unseen interactions shaped the cosmic web with far greater speed. It is also possible that inflation operated under different conditions than currently believed, or that the transition to dark energy's dominance altered large-scale structure formation in ways not yet incorporated into theory. Whatever the explanation, the discovery of structures appearing too large and too early underscores a profound truth. The universe is still revealing fundamental aspects of itself, and our current models, though powerful, are stepping stones rather than final answers. These colossal cosmic features serve as reminders that, even with centuries of astronomical progress, humanity remains in the foothills of understanding a universe whose scale and complexity continue to astonish the mind. To explain how such gigantic cosmic structures could exist despite the theoretical limits imposed by the standard model, cosmologists have explored modifications to the earliest chapters of universal history, especially the inflationary epoch that occurred fractions of a second after the Big Bang. Inflation was originally proposed to solve several problems in cosmology, such as why space appears so uniform across vast distances and why the universe is nearly flat in shape. This brief but extraordinary period of exponential expansion would have smoothed out large irregularities while magnifying quantum fluctuations into seeds for later cosmic structures. Yet, if inflation behaved differently than assumed, lasting slightly longer, happening at a different intensity, or operating under alternative physical mechanisms, then it could have generated density variations large enough to eventually form structures billions of light-years across. In that case, the massive walls and filaments we observe today might be relics of the primordial universe, fossils of inflation embedded into the cosmic web. At the same time, dark matter may have played a more influential role in the early universe than is currently understood. According to the standard model, dark matter acted as the original scaffolding for visible matter, drawing gas into gravitational wells where galaxies eventually ignited into stars. But if dark matter possessed properties that evolved over time, such as interacting more strongly with itself in the past, then its gravitational influence could have accelerated structure formation, creating larger, denser regions sooner than expected. Theoretical variants such as warm or self-interacting dark matter are actively studied to determine whether different behaviors in the early universe could explain the unexpectedly large cosmic patterns. Some researchers consider more dramatic possibilities. Perhaps the universe is composed of vast cosmic domains with differing physical conditions, separated by large-scale transitions imprinted during inflation. In such a scenario, the distribution of galaxies and gamma-ray bursts might reflect boundaries or interactions between these primordial domains. These ideas connect to multiverse theories, where inflation produces countless bubble universes, and our observable cosmos constitutes only one region within a much greater structure. If true, the largest patterns we see might be clues to physical processes extending beyond our cosmic horizon. Modified gravity remains another pathway of investigation. While Einstein's general relativity describes the observable universe with remarkable accuracy, it is possible that gravity behaves differently on cosmological scales. Some models propose that the force weakens more slowly over large distances, enhancing the ability of matter to cluster. Others suggest that gravity could have multiple components, or be influenced by extraspatial dimensions as predicted by string theory. In such frameworks, the early universe might have supported rapid assembly of titanic structures far exceeding standard growth rates. Any of these revisions altered inflation, evolving dark matter, or modified gravity could help reconcile observations with theory, but each faces its own uncertainties and must pass increasingly stringent tests from ongoing surveys. Astronomers today use deep sky mapping projects to precisely track the distribution of galaxies, galaxy clusters, and gamma-ray bursts across space and time. These observations allow cosmologists to test whether giant structures align with predictions or require entirely new physics. For instance, advanced simulations of the cosmic web have progressed dramatically, modelling billions of galaxies and the dark matter framework underneath them. If simulations based on known physics consistently fail to produce structures as large as those observed, the case for new theories grows stronger. Meanwhile, the cosmic microwave background, the ancient radiation left behind from the Big Bang, offers insight into the earliest density fluctuations. Any hints of large-scale anomalies in those patterns might correlate with giant features in the modern universe, suggesting continuity from the earliest moments. Yet so far, while some anomalies exist, nothing has definitively confirmed or refuted these ideas. The challenge lies in the complexity of interpreting structures that span such vast distances and timescales. Cosmic evolution blends processes from every stage of the universe into the results we see today. What remains certain is that discoveries of enormous structures push the limits of cosmological theory and invite a deeper curiosity about the fundamental rules shaping our universe. We are reminded that the observable cosmos is still an active laboratory of discovery, confronting scientists with evidence that may demand a profound rewrite of our understanding of space and time. These colossal features imply that the story of cosmic formation is far from complete. The universe continues to surprise us with hints that its earliest moments were richer, more turbulent, and more structurally ambitious than science has yet fully grasped. Solving these puzzles will not only illuminate how galaxies formed into their breathtaking arrangement, but also draw us closer to comprehending the ultimate nature of matter, energy, and the vast architecture of the universe itself. One of the most remarkable aspects of observing the universe is that every glance into the night sky allows humanity to look backward in time, witnessing objects not as they exist today, but as they appeared long ago. This is because light, despite its incredible speed of 300,000 kilometers per second, requires time to travel across vast cosmic distances. When we observe the moon, we see it as it was about 1.5 seconds earlier. The sun appears as it existed roughly 8 minutes ago. If we turn our telescopes toward the nearest major galaxy, Andromeda, we glimpse light that left its stars more than 2.5 million years before reaching Earth. The farther into space astronomers look, the deeper into the universe's history they penetrate. Some distant galaxies visible to modern telescopes emitted their light when the universe was in its infancy, forming its first generations of stars. By studying these ancient sources of light, scientists reconstruct the timeline of cosmic evolution, piecing together how matter transformed from a nearly uniform sea of gas into complex structures such as galaxies, planets, and eventually living beings. This principle becomes especially powerful with the help of instruments like the James Webb Space Telescope, which can detect faint infrared light stretched by billions of years of cosmic expansion. Infrared observations allow Webb to study galaxies that existed when the universe was less than 1 billion years old, revealing an era previously hidden from view. Every photon captured from these great distances carries a timestamp evidence of conditions that prevailed when it first began its interstellar journey. The concept of look-back time is central to cosmology. The greater the distance, the older the information carried by light. This is why astronomers describe objects not only by how far away they are, but also by how far back in time we're seeing them. Light from some of the most distant known galaxies has travelled for more than 13 billion years, bringing us imagery from when the cosmos was still in its earliest developmental stage. But this cosmic time machine effect extends even further. Beyond the most distant detectable galaxies lies the cosmic microwave background, CMB, a faint glow permeating the entire sky. The CMB is the afterglow of the Big Bang itself, produced when the universe was only about 380,000 years old. Before that epoch, the cosmos was filled with hot, dense plasma that prevented photons from travelling freely, meaning no light survives from earlier times. The CMB therefore represents the oldest observable light in existence, a limit beyond which telescopes cannot see directly, though neutrino and gravitational wave observations may eventually provide glimpses into even earlier moments. The farther astronomers push observational boundaries, the more dramatic the evolution of cosmic structures appears. Young galaxies discovered at extreme distances often appear small, irregular, and intensely active, churning out stars at far higher rates than galaxies today. These observations challenge theoretical models of galaxy formation, which sometimes struggle to explain how such advanced systems could exist so soon after the Big Bang. Yet the universe repeatedly defies expectations, suggesting that the processes shaping matter were far more dynamic in their early stages than once believed. This look-back capability also helps scientists track the chemical enrichment of the universe. By examining the spectral fingerprints within ancient light, researchers can determine which elements were present at different epochs. The earliest stars were composed almost entirely of hydrogen and helium, the simplest elements produced in the Big Bang. Over billions of years, successive generations of stars forged heavier elements in their cores, dispersing them into space through supernova explosions. Observing galaxies across time therefore reveals the gradual transformation of the universe from primitive simplicity to chemical diversity capable of forming planets and life. But cosmic look-back has another significant implication. When we study distant galaxies, we see them only as they were long ago, never as they are now. For all we know, some galaxies observed at extreme distances may no longer exist, or may have changed dramatically in the billions of years since their light began travelling. Our view of the cosmos is essentially a mosaic constructed from scattered pieces of history, each representing a different moment in time. The night sky is not a snapshot of a single instant, but a composite of scenes filmed across billions of years. Although this introduces challenges for understanding the present state of distant objects, it also offers a priceless advantage. By collecting enough snapshots from different distances, astronomers can build a continuous narrative of the universe's transformation. In essence, the cosmos acts as its own historical archive, storing records not on parchment or digital memory, but in beams of ancient starlight. Human technological progress has opened more and more of that archive, enabling us to read chapters of the cosmic story once believed forever inaccessible. Thus, when scientists speak of observing the deep universe, they're truly exploring the past. Every distant point of light is a message from long ago, illuminating a timeline that stretches back almost to the birth of time itself. Through this extraordinary interplay of space, light and time, we gain insight into where the universe came from, and perhaps clues to where it is headed. Distance in the universe is never as simple as it might first appear, and the deeper astronomers peer into space, the more they confront counterintuitive truths about the relationship between distance, time, and the expansion of the cosmos. Light from remote galaxies can take 12 or 13 billion years to reach Earth, which might suggest those galaxies are roughly the same number of light-years away. Yet the situation is far more complex due to the ongoing expansion of space itself. While photons were journeying toward us for billions of years, the universe continued stretching, increasing the separation between those galaxies and our own. As a result, objects whose light has been travelling for 13 billion years are now estimated to be about 30 to 46 billion light-years away in actual present-day distance, depending on the specific calculation method and underlying cosmological parameters. This difference arises from the concept known as comoving distance, which accounts for the fact that galaxies are not moving through static emptiness, but are instead embedded in space that dynamically expands. Because expansion accelerates over time driven by dark energy, the farther a galaxy is, the faster it recedes, sometimes exceeding the speed of light relative to us. Although this sounds like a violation of relativity, it is not. The galaxies themselves are not moving through space faster than light. Rather, the space between us and them is expanding. This subtle but crucial distinction allows for the possibility that countless galaxies are already beyond a so-called cosmic event horizon, a boundary beyond which emitted light can never overcome expansion enough to reach us, no matter how long the universe continues to exist. These galaxies are, for all practical purposes, lost to observation forever, even if they are technically still part of the same universe. This leads to a peculiar reality. The observable universe represents only the region from which light has successfully reached us since the Big Bang. Beyond this horizon lies the unobservable universe, potentially vastly larger and still growing beyond our sight. The observable region can therefore be imagined not as the totality of existence, but as a sphere defined by the limits of light travel time and the accelerating expansion of space. The paradox deepens when astronomers attempt to assign a single distance to a faraway object, because distance itself changes depending on which moment in cosmic history is referenced. There is light travel distance, indicating how long photons have been en route. There is proper distance, referring to the current separation between us and the object. There is angular diameter distance, which describes how large an object appears in the sky and can even decrease with extreme redshift because ancient galaxies appear smaller despite greater distances. And there is luminosity distance, tied to how brightness diminishes with expansion-stretched space. Thus, when cosmologists describe a galaxy as being a specific number of light-years away, they must clarify which definition applies. What feels like a straightforward measurement becomes a complex interplay of geometry and time. These complications stem from one profound fact: the universe is not merely a container in which matter moves. It is an evolving dynamic fabric whose shape and scale shift continuously. Understanding an object's true placement in the cosmos therefore requires unraveling how much the universe has expanded during the time its light has been traveling. Observing distant galaxies effectively means observing younger versions of those galaxies, frozen in their long-past states. Yet when theorists model their locations today, they find that many have moved far beyond their apparent position, carried outward by expansion at velocities unattainable by motion alone. Some galaxies observable in deep sky surveys already exist beyond the horizon for future light emission from them to ever reach us. In other words, we may see them now only because their earlier light is still catching up, but anything they emit from this point forward will remain forever out of reach. This introduces a bittersweet consequence. As billions of years pass, the observable universe will shrink not physically, but perceptually. Galaxies currently visible near the edge will fade away into unobservable isolation, leaving only the local group gravitationally bound together. Astronomers living in the distant future might see a universe that seems empty, static, and isolated, completely unaware of the majestic cosmic web once visible. The expansion of space thus hides the universe from itself. Our current era happens to be uniquely blessed. We exist at a time when technology allows us to reach deep into the cosmic past, yet before accelerating expansion erases much of that view forever. Decoding the relationship between distance and time is therefore not just a technical exercise, it is a window into universal history that is rapidly narrowing. Each observation represents a fragile opportunity to learn about distant realms that may soon, due to unstoppable cosmic forces, drift into a darkness from which no signal can return. As the universe continues to expand at an accelerating rate, humanity faces an extraordinary and somewhat melancholic realization. Much of the cosmos we can observe today will one day slip out of sight, not because it ceases to exist, but because the relentless growth of space will carry distant galaxies beyond the reach of their own light. This means that astronomical knowledge itself is tied to a limited window in cosmic history, our current era. Galaxies at extreme distances are already moving away faster than light due to expansion, and as time progresses, more and more of them will cross the event horizon imposed by dark energy, making their future signals forever inaccessible. The observable universe will shrink in practical terms, not by collapsing inward, but by allowing remote regions to fade into unreachable darkness. Future astronomers, living perhaps trillions of years from now, might see only the remnants of our own local group, unaware that countless galaxies once filled the night sky. Without the cosmic microwave background or bright beacons like quasars and gamma-ray bursts to reveal the universe's origin, they may never deduce the true nature of the cosmos. A civilization emerging in such a distant epoch could believe the universe is static and small, just as humanity assumed before the discoveries of the 20th century. The grand truths revealed by cosmology might eventually become unknowable, not from lack of intelligence or curiosity, but simply because the evidence will fade away with the expansion. These limitations underscore the importance of present-day research and observation. We exist at a unique crossroads, where technology allows us to peer billions of light-years into space while cosmic expansion has not yet erased the clues to our origins. The more we learn now, the more knowledge will endure into the far future through records and scientific archives that later beings might discover, potentially preserving our understanding long after the evidence becomes invisible. Yet even today, measuring the universe remains a daunting challenge. Instruments must distinguish signals that have been stretched, dimmed, and distorted by billions of years of travel through expanding space. Distances are inferred through complex methods such as redshift, standard candles, gravitational lensing, and baryon acoustic oscillations. Errors in interpretation can propagate through cosmological models, leading to debates over the Hubble constant and discrepancies between measurements of the early and late universe. These uncertainties are not signs of failure, but rather markers of the frontier. Our models must constantly adapt to new data. As tools like the James Webb Space Telescope, the Vera Rubin Observatory, and next-generation gravitational wave detectors come online, they will extend our reach deeper into space-time, uncovering new mysteries while refining what we know. One open question is whether dark energy remains constant or evolves over time. If its influence changes, the future of cosmic expansion could differ drastically from predictions. Some theories propose a gradual weakening of dark energy, which might someday allow gravity to regain dominance over smaller scales. Others suggest the opposite. Dark energy could grow stronger, leading to a catastrophic future scenario known as the Big Rip, in which acceleration becomes so extreme that it tears apart galaxy clusters, then galaxies themselves, then stars, planets, and ultimately even the atoms from which matter is composed. Though such a fate lies hundreds of billions of years away if it is possible at all, it illustrates how essential the study of dark energy is for anticipating the universe's destiny. Regardless of the details, one thing is certain. The cosmos that future observers perceive will look very different from the universe we know today. The brilliant tapestry of galaxies, filaments, and clusters spread across billions of light years will slowly unravel from sight as expansion drives them beyond communication. Cosmology teaches us that the view we enjoy, rich with evidence of the Big Bang, dark matter, and the cosmic web, is temporary. Every night skies a momentary snapshot of a universe in flux. Paradoxically, the laws of nature will ensure that many truths we uncover will eventually become impossible to verify directly. Thus, our era is not only a time of discovery but a time of preservation. We are among the last beings who will be able to document and understand the universe while its structure is still visible. In this sense, the cosmos emphasizes both the fleeting nature of knowledge and the extraordinary privilege of existing now, while the universe still reveals its story to those who seek to read it.